So today I'm going to be talking about efforts to develop a directed homotopy type theory. Some of you maybe have seen me talk about this before. I've talked about it quite a bit, but now I'm going to be talking about some further work. Okay, so there we go. Okay, so this is the outline. So I'll just introduce some of the motivations, mostly coming from applied mathematics. And then I will talk a little bit about directed homotopy theory, because that's one of the motivations and it's not so well known. And then I'll talk about a first attempt that's mostly contained in a paper that I have published, and then a second attempt, which is what I am working on now. Okay, and I also want to say before I begin that I would really love it if anyone asks any questions that they might have throughout the talk. Okay, so the goal, as the title suggests, is to develop a directed type theory or a directed homotopy type theory. And the idea is that we want to, like the really long-term goal is to formalize theorems that we might have in higher category theory and also in directed homotopy theory. So there are these kind of two different motivations, both higher category theory and directed homotopy theory. And directed homotopy theory is relatively young subject, but it's very interesting because it has a lot of interesting applications. So one is about semantics of concurrent processes, and another one that people might be interested in is about rewriting. Okay, so just to give a kind of technical idea of what we're trying to do here that I will explain more in future slides, is that we want to make this type theory directed by introducing a notion of directed paths via a type former that I'm going to call hom, like homomorphisms in a category, that we add to Martin-Löf type theory. And another criteria is to automatically be able to transport along terms of this hom type. Just like if you're familiar with homotopy type theory, you can always transport along terms of the identity type. And we also want to formulate hom so that it doesn't collapse to the identity type, which is something that often happens in many attempts that I have made. Okay, so just to kind of go back to the beginning, if you're not very familiar with homotopy type theory, this has an identity type former in it. That's I'm writing here as id. Can people see my mouse? I wonder.
No, you need to use a pointer like this.
Okay. And now can you see it?
I cannot see it.
I see. Okay, here we go.
Now I can see it. Yep.
Like this. Okay,
yep.
Thank you. All right, so the identity type former that we have in Martin-Löf type theory, you might call it symmetric or undirected, since for any type T and any two terms A and B, we always get a function like this that takes an identity from A to B to an identity from B to A. So we can invert any identity, or you might call it a path, thinking homotopically, to obtain a path in the other direction. Okay, so as I suggested, we can think of these terms of the identity type as undirected paths. And now we want to devise a type former that behaves as similarly as possible to the identity type, which is more like directed paths. So we have everything that we have with the identity type except for the possibility to invert these paths. That's the goal. Okay, and then semantically, what are we trying to capture? Well, in homotopy type theory, if you're familiar with the semantics of homotopy type theory, they lie in higher groupoids, or technically you might call them Kahn complexes and related mathematical objects. So these are like categories that have many, many levels, so not just objects and morphisms, but also morphisms between morphisms and morphisms between those morphisms, all the way up, such that all of them are invertible. And by developing a directed type theory, we want to extend this theory to one where we have also non-invertible morphisms. But there are two ways to do this. So one is by kind of targeting higher categories. And those are, like I said, we have like morphisms all the way up. And of course, in a category, your undirected paths, which you would interpret as just the isomorphisms, are contained in the directed paths, by which I mean the morphisms. So we have this relationship between the isomorphisms, the undirected paths, and the morphisms, the directed paths in a higher category. And there's another subject which I mentioned already, directed spaces or directed topology, directed homotopy theory, where we see the opposite relationship. We have a notion of directed paths, and we also have a notion of undirected paths, which I will explain in a second, and they have this opposite relationship. So there are two. So I mean, just want to maybe make the point that it's not just higher category theory that we're targeting, but other mathematical theories of directed things. Okay. Yes. Someone raising their hand.
Yeah, and we'll be on the higher category theory path, or are we going to be on both in this talk, or we're going to be on this talk?
Yeah, so I think I will kind of phrase things more in terms of higher category theory since it's more familiar. But the, I guess, design choices I'm making are really focused on directed homotopy theory, or at least making that one possibility so that we can, by setting up the type theory in different ways, just like kind of tweaking things, we can either describe higher category theory or directed homotopy theory.
Thanks.
Yeah, no problem. And okay, so first, before we get to the actual type theory, I want to talk just a little bit about directed homotopy theory, or directed topology, directed study of directed spaces, since it's not so well known. So a directed space is just, I mean, there are many concrete definitions, but just roughly, they're all trying to formalize this concept of just a space, a topological space, together with a subset of its paths that we mark as directed. So for example, here we have the circle, so that's a very good topological space, maybe the first one that you learn about. And if we want to like model maybe something kind of going around the circle, I want to say that the paths in this space, so like a path is, you know, some path from a point like here to a point like one here. So we want to say that the paths that maybe go clockwise around the circle are allowed, and the paths that go counterclockwise are not allowed. So we can illustrate that with some arrows like this. So that's an example of directed space. And one of the main reasons for the development of directed topology or directed homotopy theory is because you can maybe not easily, but very naturally represent concurrent processes as directed spaces. So here's an example of that, which I've lifted from this project by Fibrations, if I'm pronouncing correctly, and Gubo and other authors. So, okay, so for example, let's suppose that we have two processes, A and B, running concurrently. And so we can represent this by thinking about all the possible states of A and all the possible states of B, and then taking all the possible states of them running concurrently as just pairs of a state of A and a state of B. So here we have the initial state of A and the initial state of B, and the final state of A and the final state of B, which is supposed to be the final state of the whole concurrent program. And let's suppose that we just have this these two simple linear processes. So we can think about particular programs that we might give A and B. So let's say that A first does the following. So we've got two, in addition to the two processes, two memory locations M and N, and this is kind of the problem that you're always worried about when you're thinking about concurrent processes, whether like process A modifies the memory location before process B, or the other way around, and if unintended things can happen if some, say, memory location, the value in the memory location is altered in a weird order by different processes. Okay, so we have say two memory locations, M and N, and in the language for concurrent processes, we usually have instructions, say, to lock or unlock two different memory locations. So A is not doing anything interesting other than locking and unlocking these memory locations. But let's say that A, it first wants to lock memory location M, then lock N, then unlock N, and then unlock M. And suppose that B wants to do basically the same thing, except it first wants to first wants to lock N, and then M, and then unlock M and unlock N. So they're both locking two guys, but in different orders. Well, just by the meaning of this lock and unlock instruction, there are certain states that can't be reached by this these two concurrent processes. So for example, in the region where A has locked A, so we can kind of think like A has locked N. So we can kind of think that A kind of has grabbed a hold of N here in this rectangle of states here. Then B cannot itself lock N, right? So A has a hold of N, so B can't access N. So all of these states here in white are not possible. And similarly, all these states here in white are not possible. And then you might ask some things about this program. So first of all, you might ask which states are safe, in the sense that from which states can you reach your desired final state. So all the states in this gray region here, this square, are not safe because you can't continue on to reach this final state without going through some of these impossible states. And similarly, all the states here in this square are unreachable. So there might be a situation in which you can kind of clean up your program by removing the possibility that these states or that you're maybe accounting for the potentialities of these states being reached. And then you can see to some extent that there are two basic paths, two basic traces of execution from the initial state to the final state, one that goes kind of over the cross and one that goes under the cross. So all these kinds of things, the safe states, the unreachable states, the fact that there are kind of two basic paths are very homotopical kind of things to consider. And indeed, I didn't say it explicitly, but this gray area here around the cross naturally has the structure of a directed topological space. So first of all, it's just a topological space as a subspace of the plane R2. But it also gets a direction because if we're thinking about traces of execution, the traces of execution, the paths that we're interested in through this space, can only go either to the right or up. So we can't have paths that go, we can't have traces of execution that go like this, for example. So these kind of allowed traces of execution give our space the structure of a directed topological space. Okay. Oh, and I had these colors here. So these are the non-safe states. Those are the unreachable states. And these questions are very homotopical in nature. They're all about paths. Are there any paths here to the final state? And how many paths are there from the initial state to the final state up to homotopy? Okay. So we also have some less developed but still interesting motivation coming from, say, term rewriting systems. So here you might think of a type n, the natural numbers, as not just consisting of like 0, 1, 2, et cetera, but all of these possible expressions that we can build up and then that we can perhaps rewrite to simpler expressions. So then the natural numbers become not just a set, but a kind of directed space where these are our points and these, where these guys are our points and these arrows are our allowed directed paths. And if we're maybe doing type theory to study these kinds of things, we might be interested in families or dependent types on the natural numbers for which rewrites from one term to another in these natural numbers with all the terms included induce rewrites of this type to this type. Okay, so now that I've gone through the motivation, I'll start talking a bit about the attempts to develop a type theory. Does anybody have any questions in the meantime? Okay. So for the first attempt at the type theory, we have the following rules, and maybe I'll write a little bit on this now. So we want to kind of build a scaffolding for this type theory with notions of core and op. And now I think it will, I mean, we can have the motivation of directed homotopy or directed spaces in the back of our heads, but it might make sense for most people to think more about category theory, because it's, I think, much more familiar to most of us. So in order to get a hold of the directedness, we need to be able to discuss, say, the core of a type, which is analogous to, say, the core of a category, where we just throw away all the non-invertible morphisms and just keep the largest groupoid that's living inside that category. And we also want to, for any type T, we want to have an opposite type that's like the opposite category, where we invert all the morphisms. And then we'll need to have these kinds of functions that takes any term of the core of a type T to some term of T itself. And similarly, there's should be a function from the core of T into the opposite of T. So the core of T includes into both T and the opposite of T. Okay, and now with this scaffolding, we can introduce the hom type. And I'm giving in each of these slides also the identity, the formation rules for the identity type. Yes?
So you're given an explanation on those types in terms of categories, but what would they look like in terms of directed spaces?
Yeah, so yeah, exactly. So for directed spaces, we can have basically the same thing. So you can, the core would be the same space, and you would change the set of morphisms or of paths that you're allowing. And so the T core would have the same underlying space, and the new directed paths would be those that are invertible, like all of those for which its inverse as a path is also marked as directed.
So,
oh, sorry, what am I saying? Not core, but that would be op. Oh no, sorry, that would be core. Sorry.
So just a second. So we're throwing away all the directed ones, or we just no longer identifying, no longer picking up the directed ones, and everything is undirected. Everything undirected is directed. Sorry.
Yeah, exactly.
Am I throwing away paths, or am I keeping all of them and extending the directed ones?
Yeah. So the core, with the core, you throw stuff away. So you only keep the ones whose inverse is already directed, and you throw away all the ones whose inverse isn't in your set of directed paths.
Thanks.
So so for the circle where we say all of the, like, say, constant or clockwise paths are okay for us to travel along. The core of this guy would just have only constant paths left as those directed ones. So that one would be very trivial. Okay, and for op, we would just take the subset of directed paths and then look at the related subset of all the inverted paths, and then we would also have inclusions here. So someone's saying, do we assume things about T op or T core op? So not yet. So this works without those kinds of axioms, and those kinds of axioms would make the difference between, well, maybe higher categories or directed spaces or other notions of directed things. But yeah, in the second attempt, I will talk a little bit about those axioms. Okay, any other questions before I move on? Okay, so for this hom type, the formation rule looks like the following. So here I've written the identity types. Hopefully most people are familiar with this, and then this isn't too hard to understand. So, okay, we've got a type T, and we want to have 2 points, S and T, just like the identity type. We want to talk about a path from S to T. And T is just another type T, but we want S to be in the type T up, because we want this hom type to be, like, if we think about transporting it along these two variables, we want to be able to transport it forward along T and backwards along S. Okay, and for the introduction rule, so normally we just have, if we have a term T of a type T, and we have this reflexivity term. And now in this new directed world, oh, this is a typo, of course, shouldn't be there. We want to talk about something like a term of TT, but if you remember from the previous slide, let me go back. If we want to put T here and T here, T should be coming from T up, and then the second T should be coming from T, but that doesn't make any sense because those are not the same types. But there's kind of one type, I mean, we haven't said anything about it being the intersection of the two, but morally it's kind of the intersection of the two, T core. So we want to restrict our attention for this introduction rule just to terms of T core. And then we can put here the inclusion of little t into T up, and here the inclusion of little t into T. And this is then well typed, and then we can say that there's an identity morphism between these two guys. Okay, now this is a bit more complicated. We have an elimination and computation rule, and there are actually two of them coming from the directedness of the kind of, well, the underlying homotopy theory that we're trying to capture. Okay, so let's look at this. So of course there are maybe arbitrary contexts here that I have omitted, so this is easier to read. So suppose we have a type T. Now normally we say that if we have some arbitrary path, or so, let's say a dependent type, dependent on an arbitrary path in T, and it's inhabited on the reflexivity paths, then it's inhabited everywhere. Now here in this directed version, we have almost the same thing. So we have a homomorphism that's not between any two arbitrary terms, but between one which is coming from the core here, and then an arbitrary term. And with all this information, if we have a dependent type depending on all that stuff, and if we have a inhabitant of the dependent type on the identity homomorphism, and here to make it well typed, S has to be in T core, then we will also find an extension of that to an inhabitant of this dependent type on all of these morphisms, but still just the ones that start at a guy in the core. Okay, and then this computation rule here is of course just saying as usual that if we try to get out the data, the same kind of data that we put in, then it coincides. Does anybody have any questions? Yes?
Okay, hope I've got the right microphone here. In the identity type, why are you using T rather than T core as the types of S and T? It feels to me like that should suggest that you can have that both the arguments of the identity type are respecting the directed structure.
Okay, yeah, so you mean up here in this rule?
Yeah. And
yeah,
the previous rules about formation and etc.
Yeah, that's a very good point, and I should have illuminated this a bit more. So as I will say in a few slides, if we put both the identity and hom type together in this type theory, they unfortunately coincide, at least on well, in places where we don't want them to coincide. So these two type formers, I'm not putting into this, or I mean, you certainly could, but then they would coincide, but I'm not thinking of them really as being in the same type theory. I'm thinking of them as just this is from a different system, Martin-Löf type theory with the identity type, and this is a new, just separate system, Martin-Löf type theory with the hom type.
Okay, yeah, that makes sense. Thanks.
Yeah, thanks for allowing me to clarify that. I should have made that clearer.
So
okay,
follow
but we
up?
will see something very, very similar to this suggestion in the second attempt. So that might answer the question as well. Yes?
But will we be able to isolate some of the paths and kind of call them identities, like the invertible ones or something like that?
Yeah, exactly. Yes, yeah, we could. But I guess I will maybe talk about a bit more about this in the second
Okay.
attempt, which is like this, but more well-formed, I guess. Right. Okay. So we have these hom types, which have this elimination rule. It's very similar to the identity rule, but where we can kind of just, you might think of this as just allowing us to extend forward along this variable t. So we're extending our inhabitant little d forward along these guys t. And so we also have left elimination and computation. So here is the same thing as before in this gray box. And in the blue box, it's just the analog. So now we want to restrict to homomorphisms that begin at, end at a guy in the core, but could begin at anything in T-op. And if we have some dependent type on this, and we have some inhabitant on the identity homomorphisms, then we can extend this in some sense kind of backwards along S to get an inhabitant of any D of any path ending at a guy in the core. Okay. So with this, we can, it's built just to be able to do transport along elements of this hom type. So if we have still, we of course, we need something beginning at a guy in the core and ending at anything. We have a path between them and we have an inhabitant. There should be the op here. There's a tiny typo here. If we have an inhabitant over the first guy, then we can transport that over to an inhabitant over the second guy. And just using this, we can compose any two paths. So if we have a path from R into a guy in the core and from this guy into the core into a term T, then we can compose them to get a path from R to T. Okay, so we have an interpretation, should have said interpretation into cat here. So we have an interpretation into the category of categories in the way that you would expect. So we represent, just to kind of spell it out, we represent the types by, like a type in context gamma, we represent as a functor from gamma into the category of categories, the one category of categories. We represent dependent terms as natural transformations from this functor, which takes everything in gamma to the terminal category. And so in particular, if gamma were the empty context were just the terminal category itself, then a term would just be an object of T. And then we represent T core as just the objects of T. So this is maybe a bit strange for this. I'd think of T core before as being like the core of a category, like the maximal subgroupoid. And I think that this interpretation would work for that, but interpreting type theory is quite an awful, the proofs that you write down are quite awful to read. So just interpreting T core as just the objects without any morphisms at all, except for identity morphisms, it makes the proofs a little bit easier to look at. Here, this is also a typo, sorry. So T op is just represented by the opposite of T, the categorical opposite that we normally think about. And the hom type is represented by this functor, the normal hom functor, from the opposite of the category T to the category T2 set, thinking of that as a discrete category. And then these canonical terms are just represented by the identity morphism. And as I kind of suggested when I was talking about the left and right computation and elimination rules, this is coming from the fact that if we look at the sigma type, and hom here should be not so small, if we look at kind of morally the sigma type of xy of hom xy, this is the twisted arrow category, if some people have heard of that. And what's happening here is that if we're, say, given a homomorphism in the category from x to y, there are two arrows from an identity to f. So if we're thinking about this elimination rule as kind of trying to extend inhabitants living over identities to inhabitants living over arbitrary morphisms, then there are two, given a guy f, there are two possible identities which you might try to extend from. So there's one of x, one of the domain, and then you can extend to f by post-composing that guy with f, or there's the identity on the codomain, and you can try to extend that to f by pre-composing that arrow with f. So that's kind of just a few words, an intuition behind why there are both the left and the right computation rules. Okay, so does anybody have any questions about what I just talked about there before I continue on? Yes?
So just a quick one. So foundationally, how many universes do you need to make sense of it? Is it just one, or do you need two?
Yeah, I don't know how you count them, but maybe two. So you're doing everything in the two category of categories, but then internally the actual universe that I'm using is the one category of categories. And so I like using two Grothendieck universes.
Okay,
there.
thanks. Sorry about that.
Yeah. Yeah, and so yeah, I guess in the type theory as I presented, there isn't a universe in the type theory that I have to interpret explicitly, but then I am using a universe semantically to interpret these dependent types.
Okay, thanks.
No problem. Okay, so this was like a simple setup, and I think the rules for the hom type are quite correct, if I say so myself. But the kind of initial setup, this op and core business, is quite problematic in the way that I gave it. So first of all, there are no introduction rules, well, especially for T-core. Maybe you could say there's an introduction rule for T-op in some sense, but there are none certainly for T-core, and then also maybe none for T-op. So if we look at, say, like the initial semantics, like the actual thing that's generated inductively by these rules, then T-core and T-op will be empty. And so I think this is a very interesting distinction between like a mathematical theory and a computer scientific theory, that a mathematician maybe thinks of these rules as like the rules for group theory, defining the category of things that satisfy them. But a computer scientist maybe thinks more about like the actual syntax generated by these things. So if you have more of a computer scientific point of view, then this is certainly very bad, because there's nothing in these two types if we're thinking about the initial semantics, the syntax as it's generated inductively by the rules. Okay, yes?
Can you give us maybe a quick intuition as to why the type the two identities and the paths collapse? Like what kind of argument shows that?
Yeah, so basically if we just go back, if we go back to these rules, then if you, okay, so maybe you also want to have some relationship between like core and op-core and stuff like this. But if you have the normal ones that you would expect, then if you just think about, if you replace T with T-core, and then for example here you would get like T-core, but if you say that core is equal to core, then you would have here T-core, and then this whole rule becomes exactly the same as the identity rule. It doesn't look any different. It's just the identity, the elimination and computation rule for the identity type on T-core. So then hom for two guys from T-core and identity for two guys on T-core, they have the same defining property, so they become the same. And I mean, maybe this has interesting interpretations, but certainly, like, if you're thinking about category theory, if you're trying to interpret this in category theory, of course, every term should come from the core, right? Because the core of a category includes all the objects and just less morphisms. Yeah, so then you would, if all the terms of the core are the same as the terms of the original type, then the identity and the hom type are just the same. They have the same property.
Thanks.
Yeah, no problem. Okay, so right. So as I said, if we put both these guys, the identity type and the hom type, together into one type theory, they would all collapse to the identity type, which isn't good because then we wouldn't have directedness anymore. And then a more, for me, subtle and kind of intriguing problem is that we need an op function on the universe, or functor. I guess I'm using the word function if we were to have a universe in the type theory. So for example, in the semantics, I need to use this one functor that turns any category into its opposite. But this is interestingly, this one functor interestingly doesn't extend to a two functor between the two category of categories, or between the two categories of categories. And also we don't even get, so here we have like a one functor between the one functors, a one functor between the one categories of one categories, but it doesn't even work out so nicely for two categories. So we don't get an op two functor between the two categories of two categories. And similarly for n greater than 2. So we are missing this transformation, this op transformation. Yeah, there's maybe more interesting things to say about it, but I will stop there. Okay, and now I would talk just briefly about homotopy theory, since I'm giving this talk to mostly computer scientists, so I won't say too much about it, but maybe some of you have looked at the homotopical semantics of homotopy type theory. So in the first attempt that I just talked about, we represent hom here as a functor from some category C op times C into set, or equivalently under the Grothendieck construction as a Grothendieck fibration like this. So normally you write the Grothendieck fibration as a integral sign, but I'm writing it here as a sigma because I mean, it's basically the same thing as a sigma type. So if we kind of take the functor hom from C up to C into set and kind of just bundle all that up and think of it as kind of being dependent on C up times C, then we get a Grothendieck fibration here. Excuse me, Grothendieck, well, okay, let's say Grothendieck opfibration here. Okay, so we can think about this slightly differently here. Instead of just thinking about it as an arrow into C op times C, we can think about it as just having two arrows, one into C op and one into C. It's a tiny change. But then we can think about this situation a little bit differently. So instead of taking the sigma type here of all these homs for X and C op and Y and C and getting the twisted arrow category, we can replace the C op in both places with just C and take this sigma type of just hom XY. So this is now really like the arrow category as it's usually called. And now instead of this being like a Grothendieck opfibration to C op and C, we have here a Grothendieck fibration to C and a Grothendieck opfibration to C. So we have something that's like a dependent type, like the word fibration, if you're not familiar with it, has something to do with like being able to transport along paths here. So we have these two arrows, one of which we can transport forward along paths here in C, and one in which we can transport backwards along paths. So by kind of not trying to bundle everything up as we usually do when we do semantics of type theory, but kind of just considering it separately, we can get rid of the need to talk about C-op. We can just talk about different kinds of dependency, basically. So it's kind of an internalization, maybe, of op. This last viewpoint here was studied by a category theorist, Street, in the 70s. It's he called it a two-sided fibration, which, as I said, it's a pair of a Grothendieck fibration here, a Grothendieck opfibration here, and the pair interacts in a nice way, such that if you lift in the vocabulary of Grothendieck fibrations or transport in the vocabulary of type theory along a morphism, say in this guy, then what you get up here will not change like if you say think about it as a function from the fiber here to another fiber, it won't change the fiber over the other guy. It will leave this guy, the other guy that you're not transporting along, it will leave it fixed. And so this is exactly what should happen in type theory. If you have, say, now a morphism, thinking about our goal of directed type theory, if you have a morphism from some guy A to A prime, say here in C, then you should be able to transport, say, a type that's dependent on two of these variables, A, B, to A prime and B, without messing up this B here, right? I mean, that's just how type theory works. And so that's exactly what's captured in the notion of two-sided fibration. Okay, and so with some collaborators, we're developing a notion of directed weak factorization system based on this idea that will provide the semantics for this, or hopefully will provide the semantics for this directed homotopy type theory, just as the usual theory of non-directed, regular old weak factorization systems provides the semantics for regular homotopy type theory. Yes?
So just to see I follow, A and B are just dependencies for T, right? They're not covariant or contravariant, right? They're just two.
Yeah. So maybe I'm thinking about T as just being covariantly dependent on both A and B.
Okay,
like
thanks.
Yeah, I could have made it match the situation a little bit better. But here we can maybe covariantly transport T along this morphism from A to A prime. And then it should, of course, mess up this B here. And that's exactly what's captured there. Okay, so I can talk a little bit more about the homotopy theory side of things if anyone is interested in, but I will maybe just leave it there. Okay, so now we can start thinking about the second approach, a little bit more complicated, to this directed type theory. And so just like, let me go back a little bit, just like the kind of goal of this homotopical thing that I'm doing on the semantical side is all about trying to capture what we were previously capturing with the tool that we had in the op functor, but without using the op explicitly. Now in the type theory, we try to do the same things. We try to capture the behavior without having this op transformation or operation explicitly. Okay, well, it's relatively explicit, but this won't produce a function on the universe, say. Okay, so to do this, we are going to follow Licata, Shulman, and Riley's 2017 modal framework on the sequence calculus. I know that they're working on a version for dependent type theory, but hopefully what I'm saying will be an example of that, but they haven't published it yet. They haven't released it yet, so I'm not sure how it compares to the actual dependent type theory version. Okay, so for this, we need like a lot of layers, unfortunately, for our type theory. So the first layer is all about the modes. So we have just, so we have this two category of modes. We have just one object. You would have different objects in this kind of modal type theory setup if you wanted to have different kinds of types, which we certainly maybe could here in an extension of this, but here we just want to consider one kind of type, so there's just one object. We have two different morphisms between this one object. We have op and core. And then we have two different two morphisms, just like we had before, from core into the identity, and an inclusion from core into the op. And then we can also include equalities here, like I forget who exactly, but someone suggested. So we could have op equals 1, and anything composed with core in any order is just core itself, etc. Okay, so those were the modes, and now, yes?
Can we specialize this to one of the previous models by choosing, say, cat and star being one of the categories in there or something like that?
Yeah, that's exactly the hope. So kind of developing the syntax and the semantics at the same time. So I haven't formally connected them, but that's definitely inspired by well, this notion of directed weak factorization system that definitely exists in CAT and other notions of higher categories and directed topological spaces. Yeah, so it should be the syntactic analog of the semantics, the weak factorization system semantics. Yeah.
Thanks.
Okay, and so, oh, I also wanted to make clear, I don't think I said this out loud, but somewhere I did say, I did write that this is work in progress. So yeah, if anyone has any comments or anything to say, I would be very interested in hearing it. And of course, I have a disclaimer that some of the things might change as we try to like maybe prove things about this that we want to prove. Okay. All right. So so there we have the modes, and now we need another layer. Hopefully, all this will become a bit more clear when we get to like actual interesting things in the type theory. So we need this other layer of context descriptors. And so basically what we're trying to do is we're trying to, instead of, let me write something down, instead of saying, let me try to write something, yeah, okay. Instead of saying, as we did before, that hom depends on a guy in T-op and a guy in T, we want to say, we want to not change the types, but rather we want to say, just kind of here somewhere, what the dependency is that hom has on T in these two cases. So we would write this in the following way. The handwriting isn't looking so nice here, but something like this. So we have a kind of annotation under the turnstile that's saying that we're using X in an op way, and we're using Y in the regular old way, in a covariant way. So we're annotating the turnstile, the dependency operator or something, with information about how our type actually depends on the context. Okay, so very similarly to the tiny blurb I gave about like two-sided fibrations and stuff. So there we changed the notion of a fibration of dependency also in the semantics. Okay, so these kinds of, yes?
So we can also say that we're using a variable both covariantly and controvariantly, right? So this falls on these rules, right? So there's just kind of a language of saying covariantly, controvariantly, neither, both.
Yeah.
And similarly for core as well. Okay, bijectively.
Yeah, exactly.
Yeah.
So yeah, we could have like also that we're using X also covariantly, say. But I mean, here in this particular type, we're not.
Thanks.
Okay, so right, so we have these context descriptors that are these kinds of sentences, and so this is some kind of, I guess, sequent calculus, and they're inductively generated in the following way. So we have here all the as I'm saying below, all the variables in the context of these variables here in the beginning of the turnstile coincide with the variables in the context of our judgment. And so we can just say that, say, xi is being used in a normal way, or that maybe none of the variables are being used. And so here, hopefully it's clear, I'm using the bar to just abbreviate x1 through xn. And so if we have that x bar produces y, then x bar can also produce op y, also core y, and if it produces y and z, then it can also produce y comma z, so that we can build up expressions like this. Yes?
Do we care about the order in which they appear, or is it modulo the order and the?
Yeah, so I didn't write it here, but yeah, I guess modulo the order
Okay,
of
thanks.
the things after the turnstile. Yeah. Okay, so these, yes? Yes?
You should try to wrap up soon. Sorry.
Oh, yes. Okay, good point. Okay, so, all right, so this is getting complicated. Maybe it's okay that I will just skip all these complicated things. But so we have we have some rules that are a little bit different because of what's happening here. So we have a variable rule. So we have all the variables from gamma. We've got this guy x. We've got all the variables from delta. And if we just do kind of this obvious thing and produce x and sigma, then it's just using the variable x in the normal way. So, I mean, we're even accounting for things that we don't normally account for in usual dependent type theory. That's the idea that we're just using x and we're not using any of the other variables. So similarly, we can weaken by a type here, and this is also a typo. I should have x in row here between gamma and delta. We can also substitute. It's a little bit more complicated because we have to substitute also in this annotation here. And here we have also this modal substitution rule, which is maybe the one that you would imagine should be there. So if we have one of these two cells in the mode category, so for example, we had one from core to op, and then say we have an annotation here that's using op of x, then we can also have the same judgment in core of x. Okay, so if so maybe this is a way to say that op being variant in an op way, being contravariant on x is stronger than being equivariant, you might say, on x. Okay, and now we can define the hom type in this modal setup, and we do it very similarly to how we did it before. So we're again trying to produce hom AB given an A and a B, but in order to account for the fact that we want this hom guy to be contravariantly dependent on A, we want anything, so maybe this delta could be like A and A itself. We want this the variables from delta being used in an opposite way to how they're being used to derive B. So maybe, well, maybe it makes more sense to say delta is A and A and B and B. Okay, and then we have this introduction rule. So just like before, we were saying explicitly that A was in the core. Now we're saying that it might be dependent on some guys in delta, but only in a core kind of way, only in an equivariant way. So that's how we're kind of building in the dependency just on the core. And in that situation, we get an identity morphism. And similarly, we have a right hom computation elimination rule. And we now say explicitly that the dependency of D must be on A in a core kind of way, and on B in a regular kind of way, in a non-annotated kind of way. And that here, this inhabitant that we need must be dependent on A also in a core kind of way. So we are just removing the core that was here above the A into this this annotation. Okay, so what can we do with this type theory? So didn't think that I would have enough time, and I guess I didn't, to define the identity type analogously, where instead of the annotations where certain things had to be in the core and in the op and everything, we just make sure that everything is in the core. And then we can find an inclusion here from the identity from A to B into hom A B in the, say, in the context, which is depending on A and B in a core kind of way, in an equivariant kind of way. But we can't find a morphism in the other direction, which is exactly what we would expect and hope for. And just as before, we can still transport along homomorphisms, and we can compose homomorphisms, which is great. Still, one mysterious thing is that, so I'm following quite closely this work by Lakota, Shulman, and Riley, but they kind of couch it all in terms of these, something like a sigma type, which they call an F type. And then they kind of derive many of the rules that I gave just from those rules for the F types. But a strange thing is that these sigma types produce opposite types. So for example, if you took the sigma type of a judgment like this, where this is just the trivial type with just one term and no interesting directed or undirected paths, then you would get A op itself. So if we just stipulate that we have all sigma types, then we would get a function that turns types into opposite types. Okay, so for future work, I mean, this is a work in progress, so future work is just to finish this work. In particular, the main goal right now is to connect this formally with the intended semantics, those directed weak factorization systems that I was talking about. Also, maybe we want to understand which sigma types exist. I mean, surely some of them should. It's important to be able to do stuff that we have some sigma types, and maybe more of them will exist for different kinds of intended semantics or something like that. And then also, of course, the next steps are to think about pi types, directed univalence and its consequences, and higher inductive types, etc. Okay, and that's it. Thanks a lot for coming.
Thanks. Do we have time for a few more questions? If anyone has a question. See the smiley faces. Yep, James?
Yeah. Yeah, so I think you kind of answered this during the talk, but I didn't. Although when you said in the first system that the hom and the identity collapse,
yeah,
your reasoning there seemed to be that they collapse T-core, but to me that sounds expected. So what's the reason why that's a bad thing?
I'm sorry, could you repeat maybe the last sentence you said? I had a little bit of trouble hearing you.
Okay, yeah. So your reasoning for saying that hom and identity collapse was that if you set T to be T-core, then hom becomes identity. But this seems like a wired feature to me. So I was just surprised you mentioned it, and whether you could say any more about why you wouldn't expect that.
So I think I heard you say at the end that maybe I could say a few words about why I wouldn't expect it. I suppose, I suppose I would expect it, to be honest. I mean, since these rules are so close to the identity type rule. And so in particular, like maybe one interesting or trivial thing to think about is that if you interpreted this kind of scaffolding as, say, you just have regular old Martin-Löf dependent type theory, you could say that T-core, you could kind of interpret this into another type theory, this regular old Martin-Löf type theory with the identity type. You could say that T-core is just the same as T, and T-op is just the same as T itself, and then that these inclusions from T-core into T and into T-op are just the identity functions. Then this rule just collapses to the identity types of this rule. The hom types and their rules can be interpreted by the identity type and its rules. So yeah, so I guess this is kind of another way to explain it. So if we were to just interpret T-core by T, or if we were to replace all the capital T's here by T-core, then we find that this rule is just the same as the identity rule. So we need this kind of modal setup to kind of force a separation between these two guys.
I totally expect that once you throw in something directed, like whether you have a directed circle or something, then T-core would be something different. Like when you're talking about the circle, T-core is a very different space. So circle core is a very different space. So it doesn't seem too surprising that you get a very different result with a very different space.
Yeah, that's an interesting point. Yeah, I guess. Yeah, I guess I just haven't thought about having like higher inductive types in this first attempt, and what would happen if you tried to put in a directed circle. Maybe it would just kind of somehow formally invert all the paths to get some kind of undirected circle or something even more complicated. Yeah, it's an interesting question.
I mean, if you include, this is just me not maybe being strong enough, but if you include all the high inductive types, are you going to get sigma types as well, or is that separate? Because once you have all sigma types, right, you get the ops, and then you basically where you started, right? You can turn the op into a type level operation, and that's what you're trying to avoid, right? So
yeah, exactly.
I guess you have to be careful whether you're getting all sigma types from the high inductive types or not.
Yeah, certainly. Yeah, so I guess I'm thinking of higher inductive types in just a very simple way, just like maybe kind of an analog of like directed CW complexes, just where we maybe can glue directed lines, directed circles to directed spheres and things like that. So those certainly should be possible. I mean, those are modeled in all good models of directed spaces, and yeah, I would think by higher categories. But yeah, once we start doing like really like full-blown higher inductive types, then yeah, we don't want to include sigma types, all sigma types at least.
Okay.
Okay, thanks.
Thanks. So there's a question in the chat. If you can give a quick answer, that would be great. If not, then we can take it later. How does this compare with Finster-Nimram's type theoretical definition of weak omega categories? So if you can quickly
that's a
compare
good
it.
question. So that's quite different. Their approach is quite different. I mean, very interesting. But they kind of formally give the type of, they kind of formally maybe emulate, I mean, with a lot of differences because it's type theory and not set-based mathematics, but formally emulate the definition of Batan and omega categories. So they formally give 1 cells and 2 cells and 3 cells. If I might be a bit wrong, it's been a while since I've read it. And they formally give the rules for how these interact with each other, almost cellularly, like giving all this information, instead of hoping, as I am hoping, to give a hom type, which just with the simple elimination rule does like the identity type of Martin-Löf type theory, which just automatically, with just the simple for rules, just automatically produces higher groupoids. And so I'm hoping to kind of emulate that with this hom type, which is similar to the Martin-Löf identity type.